Good morning, grade 9s. Let's take a look at the third lesson of the space unit. And the third lesson of the space unit is going to be about the movement of the Earth and the movement of the Moon. Okay, so I've already talked a little bit about or hinted at perhaps the movements of the Earth. We're going to explore that in greater detail with this lesson. Okay, and we're going to take a look at the Moon. All right, which is the big silver-looking disc in the sky, right? You're familiar with it. First and foremost, there are homework questions for you to complete, okay? And, I've picked and chosen which questions, so you don't have to do them all, but of course, it is recommended that you complete them. That's how you solidify your learning, okay? So let's begin. Earth's motion. We've actually talked about this. This is a review. Earth undergoes two different types of motion through space, rotation and revolution. Okay? The path of Earth's orbit around the sun is not a perfect circle. It's an ellipse. You know that. An ellipse has two focal points. This is new. The sun is at one focal point of Earth's elliptical orbit. Therefore, as Earth orbits the sun in an elliptical pattern, Earth is closest to the sun at one focal point and furthest from the sun at the other. Okay, so I mentioned this in the last lesson that we did, or perhaps the lesson before that, is that sometimes Earth is closer and sometimes Earth is farther from the sun. Okay, and of course we're talking about revolution. That's the motion that we're talking about right now. Revolution, not rotation, revolution around the sun. Okay, so if we take a look here, right? The dates are listed here. So you have December, March, June, and September. Okay, and so we have two focal points. And these focal points here, instead of having like in a circle, we'd have one center, one focal point at the center of a circle. Instead, we have these two focal points. And the focal points are equally distant from Earth at the two ends of the ellipse. Okay, however, the sun is only located at one focal point. And that means that in December, during the winter, we're actually closer to the sun than we are in June during the summer, okay? And then, of course, as the Earth revolves around the sun, that distance changes, right? So now, wrap your head around this. In the winter, when it's cold here, we're closer to the sun than in the summer when it's warm, okay? And then of course, spring and fall, spring and autumn, they're intermediate, right? Notice that, there's a lot of similarities between the two as it sort of gets warmer, and as we know it begins to get cooler, we can kind of see that those are intermediary seasons. Maybe that's why they're often the best seasons, because they're kind of not too hot, not too cold, okay? But take a look at that. Earth is furthest from the sun in the summer and closest in the winter, okay? Now, why do we experience seasons, okay? The seasons, the hot of the summer and the cold of the winter, is not caused by the distance between Earth and the sun. So if you're looking at that previous slide and going, no, it's cold in the winter, how could it be closer to the sun? The sun is the big ball of hot fire. Why would it be colder at that point in time? Because the seasons that we feel, the temperature that we feel in each season, is not dictated by the distance between our planet and the sun. It's dictated by Earth's tilt, okay? So we know there's a North Pole and we know there's a South Pole on Earth, okay? And normally we think about, North and South, okay? North is at the top, South is at the bottom. But in fact, our Earth has a 23.5 degree tilt, okay? 23.5 degree tilt. And in the summer months, right, so June, July, August, okay, the northern hemisphere, that's our hemisphere, that's the hemisphere that we're in, is tilted toward the sun. And in the winter months, okay, that tilt causes us to be tilted away from the sun, okay? The opposite is reversed in the southern hemisphere. That's why in Australia, their summer would be in December. And their winter, even though their winters are not as typically not as snowy and cold as ours, but it's still cooler temperatures in their winter. Well, that occurs in June and July. Okay, so because of this tilt, it's not straight up, it's tilted, sunlight strikes Earth's surface at different angles. So we're going to look at that in pictures here in a couple slides, but let's get these notes down first. Okay, the amount of sunlight received at any location on the globe is a direct result of the angle at which sunlight strikes the Earth because of Earth's tilted axis. So it's not about the distance from the sun, it's about what angle light from the sun is hitting Earth at. And the more direct that light is, the more direct the angle is, well then the greater the temperature, okay? If it's at a low angle, well then you're spreading that light out over a greater area, and therefore the sunlight is less intense. If the sunlight is less intense, then the heat is less intense. If you're at a higher angle, in other words, you're getting more direct light from the sun, well then that energy is concentrated on a smaller area. Okay, and so that smaller area then receives greater temperatures. Take a look at these pictures. Okay, so you got to imagine that the flashlight here is the sun. Okay, if you're flashing that flashlight at a low angle, look at the area that light is spread across. Well, that's the same amount of energy because it's the same flashlight, but it's spread over a wider area, and so you get cooler temperatures. Whereas if you angled that flashlight directly above the land, you concentrate the light and therefore concentrate the light energy, and therefore you're increasing the heat. Now, here's what happens in our summer. Okay, so here is the tilt. So the sun is directly across from the Earth here. Okay, so we're looking at the sun, should be off the page here. All right, so we have this tilt, and so what's ending up happening is the northern hemisphere is receiving solar radiation at a higher angle for longer periods of time. And of course, the closer you get to the equator, then the higher the angle is. Okay, but we're receiving greater intensity of light for longer periods of time because the angle is a little bit higher. All right, so let's look at this this example here. This is obviously Parliament here on the bottom. Okay, and it's so the same place, the same directions, but at 3 different times. Actually, it's 4 different times of the year, but the spring and fall, it's a similar angle. Okay, so this is what we're going to see. The longest day in summer, we have the sun, okay, higher up in the sky for longer periods of time because the angle at which Earth is tilted, okay, puts that sun higher in the sky from our perspective, okay? And that means we receive a lot more direct sunlight and our days are a lot longer, and so the temperature is warmer, okay? In the spring and the fall, you'll notice that the sun's a little bit lower in the sky. It's not directly above Parliament, it's a little bit lower, and it's a lower angle. And so the length of time of our day is shorter. And so day and night are kind of almost equal, and so we notice the temperature's a little bit lower during those months. Okay, and then when we get over here to winter, look how low the angle is of the sun. And that's because we're actually, during the winter months, we're tilted because of this 23.5 degree tilt. We're tilted away from the sun. And so that angle is a very low angle. And so our days are much, much shorter in the winter. And therefore we receive a little less sunlight. Or if we receive a little less sunlight, we receive, let's say, a little less heat. Okay. So since Earth's surface is curved, a beam of sunlight illuminates different sized areas at different latitudes. Okay, so the closer to the equator, that solar radiation is hitting Earth's surface almost straight on. And so, of course, where are the hottest places on our planet? Well, they're in South and Central America. They're in Sub-Saharan Africa. They're in India. Okay, because these places are very, very close to the equator. And so no matter what the tilt of the Earth is, no matter what season it is, they're always going to receive the most amount of direct sunlight. But as the Earth curves up and we go further north or perhaps further south, okay, that curve of the Earth also spreads out the sunlight that's hitting that area of the planet. And so you're going to end up with cooler temperatures. Okay. So that would be like saying if we're talking about the northern we're talking about the northern hemisphere only, we're going to say higher latitudes, okay? So further from the equator spreads the solar radiation out, which means we get light at a larger angle, and so we get cooler temperatures. Okay, we're looking at the moon now. Okay? Now, just like the planets in our solar system, we haven't talked about all the planets yet. We've talked about Earth is the only one we've talked about, but we know we should be relatively familiar with the fact that all the planets, okay, orbit the sun, right? They revolve around the sun. Well, moons orbit planets. Now, we have one moon, okay? Jupiter and Saturn, well, they have over 60 moons. They have enormous numbers of moons. I mean, they're very big planets. We'll talk about them a little bit later. They're massive, massive planets. They have 60 moons plus, okay? We only have one little moon. We have one, actually, we have one special moon. It's our moon, okay? We may only have one, but it's ours, all right? Now, to us, that moon appears as the largest and brightest object in the night sky, okay? But that's only because it's the closest one to us, all right? The moon is not brighter than the stars in the sky. It's just because it's closer to us that it appears that way, all right? Now, the moon will orbit the Earth, in other words, go all the way around the Earth in 29.5 days, which you'll notice is very close to the length of time of a month, okay? Which is why our months are the length that they are, because that's roughly the amount of time it takes the moon to go around the Earth, okay? Now, the moon rotates very, very, very slowly. And in fact, the timing is such that when it completes one orbit around Earth, so it goes around the Earth once, okay, it actually only rotates once, okay? And that means as it's orbiting around the Earth, we only ever see one side of the moon. We never see the other side of the moon, which we call the dark side of the moon, which is actually a misnomer. It's not really dark, but we call it the dark side of the moon because we never see it. The timing is so perfect that no matter where you are on the planet, if you're looking at the moon, you will be looking at the same side of the moon, okay? So, the moon is always half illuminated by the sun. The amount of illumination you see is classified as the phases of the moon, okay? So, you've seen the phases of the moon, certainly, okay? You know what a full moon looks like. You know what a quarter moon looks like. You know what a crescent moon looks like, okay? And this is why, okay? The moon is always half illuminated by the sun, but the amount of that illumination that we see changes depending on where the moon is, okay? So if we look here at a full moon, okay, and this diagram is drawn so that the sun is in a certain place, the Earth is in a certain place, and the moon is in the correct place. So if we're looking at the full moon, okay, the sun is back here, the Earth is in the middle, and the moon is on the farthest side. And so the side of the moon that's receiving sunlight is the side that's completely visible to us, okay? Now, if we look at a new moon, that means the moon is in between the sun and Earth, and so we're only seeing the dark. So, sorry, let me rephrase that. The part of the moon that we can't see is the part that's illuminated. And so when we look up in the night sky, we do not see the moon because it's not there. The part that's hitting the sun is on the wrong side of Earth to see it. Okay? That's why sometimes during the day, if you wake up early enough, you can actually see the moon in the daylight sky because it's undergoing new moon. You won't see it during the nighttime, you see it during the daytime. Okay? And then as the moon rotates, different portions of its illuminated side are visible to us. Okay? So we'll describe those phases on the next page. Okay? The new moon is completely unlit and begins to be illuminated from the right side to the left side. So it's unlit. You don't see it at the night, during the night. Okay? You might see it during the day, actually, early enough in the morning. Okay? Now, waxing is a word that means it's increasing the amount of illumination as a new moon becomes a full moon. So if I go back, here we are at new moon, then we have a waxing crescent. So the right side of the moon to us begins to be illuminated in that sort of famous crescent moon, that famous crescent moon shape that we see. Okay. A full moon is completely lit and then will begin to decrease illumination as the shadow gets larger from the right side to the left side. Okay. Now waning means we're decreasing the amount of illumination as a full moon becomes a new moon. Okay. Now the word gibbous means the amount of light we see illuminating the moon is between half lit and fully lit. So gibbous means 3/4 lit. So we'll go back to this diagram for a second. Okay, so it's new moon. We can't see the illumination of the new moon. It's on the far side of the moon that we never see. Okay, we might see it during the daytime. All right. Then, as the moon begins to rotate around Earth, okay, we'll begin to see the waxing crescent. So the crescent part means the shape, and the waxing means it's increasing. Okay. Then we'll see the first quarter moon, okay, which is actually half the moon illuminated. We see an image of half that flat piece of the moon illuminated, okay? Then we'll see a waxing gibbous. And a waxing gibbous means it's increasing in illumination. That's what waxing means. And gibbous means 3/4 of the moon is illuminated. So where's my cursor? You can see that 3/4 is illuminated. And then we get the full moon. And then what we're going to do is we're going to work through the same stages, except instead of waxing, we call it waning, because the amount of illumination is decreasing, but it goes through the same shapes. The gibbous shape, the quarter shape, and the crescent shape, all the way back into new moon. Okay. Now, you've heard of eclipses. There's two types of eclipse. Okay. An eclipse is an event in which a celestial object moves directly in front of another. That's what an eclipse means. Okay. So in general, that's what an eclipse is. So a lunar eclipse is a particular kind of eclipse. But before we talk about what a lunar eclipse is, we have to talk about Earth's shadow. And there's two parts. The umbra is the inner shadow, and the penumbra is the outer shadow. All right, so you can see that in this diagram here as we sort of start to see what a lunar eclipse might be. Okay, so a lunar eclipse is the event in which the moon passes into Earth's shadow. So the moon isn't always directly behind Earth. I know that in this diagram it looks like it is, but there's different angles going on, and so very rarely is the moon actually obstructed by the Earth, because it's a little bit above the Earth or a little bit below the Earth. So very rarely is it actually covered by the Earth, but there's odd occasions where the moon will pass into Earth's shadow. So the sun exists on one side, the Earth is in the middle, and the moon is directly behind the Earth, and so the moon falls into the shadow. Okay, so there are usually 2 lunar eclipses every year that are safe to watch. Okay, and sometimes you might see the moon is looking reddish, and that's because some of the light is refracting. Sometimes the moon will disappear and you can't see it because you just see the Earth's shadow. You can barely see it because Earth's shadow is on it. Okay, so that's a lunar eclipse, and they're fairly common. Okay, they're not super common, but they happen fairly often, and you might be able to observe it. Okay, and that's what a lunar eclipse is, when the Earth is eclipsing the moon. Okay, now a solar eclipse is a little more rare. Okay, and what happens is the shadow of the moon falls on Earth's surface. Okay, now here's the really interesting part of the moon and the sun. The moon and the sun are drastically different sizes. Okay, the sun is enormous. This diagram is not to scale. We'll talk about the scale of these objects in a later lesson, but the sun is so much larger than the moon that it's very difficult to show in a diagram. But because the distance between Earth and the moon and Earth and the sun is different, it appears as though the moon can perfectly cover the sun. Okay? So what ends up happening is, once in a while, the moon gets exactly in between Earth and the sun, and it appears to cover up the sun. Okay, it can only happen during a new moon, okay? Only happen during a new moon, right? Like I said, that sometimes you can see a new moon during the daytime, okay? But it's very rare to see it, okay? Now, there are partial solar eclipses, okay? There are partial solar eclipses, right? That you can see sometimes. It's very rare to see a full one, okay? And in order to see a full one, you have to be at a certain location on planet Earth. So it can vary, but usually the full solar eclipse is only seen at certain places on planet Earth. And here's why. Look at the way the moon interrupts the sun. Now, this blue line is like the sun's light, and this dotted line is like the sun's light, okay? So what ends up happening is there are certain places that fall under the complete shadow of the moon, okay? They're very specific places, and then the rest of the Earth, the rest of the side of the Earth that's facing the sun at the time, the rest of the Earth that's going through daytime at that moment, sees partial eclipses. Only at this little point where the moon, where the sun is directly covering, let me rephrase that, where the sun is directly causing an umbra shadow from the moon, can you see the full solar eclipse, which looks like this, okay? Where it's the only, only certain places at certain times during an eclipse can you see the moon completely eclipse the sun, okay? And it looks like it's got this crown all the way around it, okay? So you have to be in certain places. Now, there was a solar eclipse within the last couple of years that was visible from North America, where certain places in America, in the United States, you could have looked outside and you could have seen this. However, you cannot directly look at this diagram, okay? In real life. This is what it looks like, but you cannot look directly at it with your eyes bare. And that's because there's still some solar radiation. It looks like a crown here, but that's still solar radiation, and that can damage your eyes, all right? So it's very dangerous to look directly at an eclipse because there's still some light and some radiation escaping. Of course, the President of the United States, during this eclipse, I'm going to let you Google it and look it up. During this eclipse, was observing from the White House, and he looked without sunglasses on directly up and saw this for himself. So he wanted to, I guess, verify that that's what it looked like with his bare eyes, because he has not taken grade 9 science, I guess, right? But I don't want to get too political on you there. So what you need to know, lunar eclipse is sun, earth, moon, right? In other words, the earth blocks sunlight from reaching the moon, and so the earth eclipses the moon. And sometimes you can see light refracting, which you'll learn about in grade 10, but you can see light kind of bending and refracting and causing a red color on the moon. During a solar eclipse, the moon gets directly in between Earth and the sun, and can, if you're in the right place on planet Earth, right, directly cover it. And that gives this kind of an image in the sky, right? And it's completely darkened because you are literally in the shadow. It's literally like the sun casting a shadow from the moon on certain sections of the earth, and it becomes almost very, 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 very dark. Okay, and then other places have partial light. Okay, depending on where you're located in the hemisphere that is undergoing the eclipse at that time. Okay, so lunar eclipse means the moon is covered. Solar eclipse means the sun is covered. Okay, so I think that's it for this lesson. So please make sure that you are staying healthy and safe at this time. We're approaching the near end of the course. So, those of you that have stuck with it as we get through it, good for you. I'm really, really glad to see a lot of you sticking with it. Those of you that you feel like you need to catch up a little bit, you still have time to catch up and get stuff into me to improve your mark. So please make that a priority. Second only to making sure that you keep yourself safe and healthy at this time. Okay, guys, until next time, take care. Bye-bye.